Hi. So I'm going to show you how to read in a stack as a raw data format from the Bruker software on the Titan. So I'm using a software package called Fiji, Fiji is just ImageJ, F-I-J-I. ImageJ is an open source software for image processing, which handles things quantitatively, so you can do analytical work on microscopy. I think a lot of you are probably familiar with it. Normally, when you save a stack from the Bruker software, it's its proprietary BCF format. And you have the option to also save it as a raw stack. So you'll notice the BCF format, in this case, this stack was something like 50 megs, 45 megs, and the raw is now 1/3 of a gigabyte. So there's no data compression. It takes a lot of space, but it's really useful because you can get at the raw data. It saves raw, which is the actual data, and then RPL is a text file which describes that data. So here, this text file has a few fields. Data length 1 means that it's 8 bits per pixel, basically. And it's a 344 by 480 pixel map. Those are spatial directions. And then the depth is 2048. And that's because I think it's a 0 to 20 keV energy axis, and then it's 10 EV bins, right? So first we're just going to read in the raw data. So the order in which Bruker writes it out is a little different, and so to read it in, we're going to use 8-bit. But now our width is the energy axis, our height and depth are the width and height from Bruker. Okay, so that's a little different. That'll catch you. So now it's reading the stack. Takes a little while because it's 1/3 of a gigabyte in this case. Okay, here it is. It's still catching up here. Okay. So this direction is the energy axis. This direction is the vertical spatial direction. And then this direction is the horizontal spatial direction. And what we want to do is we want to rotate the stack. So the command for that is reslice. Here under image stacks, reslice. And this is the 0 energy, and this is the 20 keV energy. So we want to start slicing it at the left. And now it works like this. So it takes a sec to parse through that. So in the meantime, you're going to also need a spectrum. It doesn't matter what spectrum you save, just any spectrum, because Bruker outputs inside that text file, if you save it as the text format for the spectrum, they tell you about the characteristics of how you acquired it. So in this case, I acquired it at 80 keV, and what I really care about here are the calibration. So this is saying that there are 10.001 electron volts per bin. So each slice this way is adding 10 EV. And then the offset is negative 469.147 EV. So the 0 slice here is not 0 EV. That is negative 469 EV. So 0 EV actually occurs about 47 slices in. Still reslicing here. Big stack. once I've got the reslice done, I usually save it as a TIFF stack, and then I don't have to go through the rigmarole of reloading a raw and then rotating it. Okay, and here is the actual stack. So here I'm setting the maximum counts. This is just the brightness contrast function, and I'm going to set the counts to 7, so the saturated 7 counts. And so you can see the different edges. So 7's too low. Let's actually set this bar a little higher. Alright, now what you want to do in order to get an element map is this element, not sure what it is, but it starts here at slice 170 and goes to about 177. So what I would tend to do is I would use the slice keeper. And I would just pull out slice 170 to 178. And if you want to think about what is the exact right slice numbers to pull, then you might want to do that. That makes a new stack, in this case only with 9 slices, and what I'm going to do is average together each of the images in order to produce an image with low signal to noise for this element. So Z project, and you can use average or sum, depending on how many counts you've got. Use average. And there's a nice image of that element. Okay, part 2. So we have our stack, and I've written myself a macro which does the same logic we were doing before. It's actually a plugin, I guess. And I'll send to Karen the source for this. But I wrote it in Python, and it just has a simple Java wrapper. And so what it does is it uses this calibration down here to know what slices to pull, and it generates a number of these element maps one by one. So here it's doing that same procedure over and over. That's our aluminum map. Carbon map, and so on. And what we're going to do now is make some RGBs from those images. So there's a plugin called RGB Composer. I think it's actually not installed by Fiji by default, so you need to install it yourself. You can just do a web search for it. It picks some random images of the ones you have open as your R and your G and your B. So what you want to do is tell it what elements you want. So in this case, I'll look at calcium and iron and silicon. And then I'll just auto scale it, let it guess what the best brightnesses are. But of course, you have brightness contrast upper lower settings so that you can manipulate this yourself. And there's my RGB. And so you can see right away we have some interesting phases there. I zoom in a little bit. Again. And that green phase really pops out. So I could select that area. And then Z profiler. Oh, I should do it on stack. So I think this is the sulfur edge. Z profiler. That gives me the spectrum of that area. So iron, little nickel, and sulfur. And then, of course, you could save this spectrum. Remember, this is the pixels energy axis, not your energy axis. And so you'll have to apply this calibration to it in order to do anything with it. So we'll save this to the desktop as sulfide.txt. And then, of course, you could drag this around to look at other areas, and it dynamically updates this. So that's very useful, especially when you're poking around to try and find things. And then you can load that spectrum using bitline K, for example. But it's just a 2-column text file. You can use Python or whatever you like. So here, for example, you will note I put the cursor here, and then down in this corner you'll read the position. So it's occurring at about 282 on the x-axis, 280, something like that. And so per this calibration, that would be 282 slices in, so it would be 2.8 keV minus 469 eV, so 2.2 eV, and that is about where the sulfur edge is, I believe. And then this is your iron K, and nickel K, copper from my TEM grid, and the silicon from some other silicon stuff around this. There's actually a slight silicon one. This is a Stardust commentary grain, by the way. And so I had actually written in this software transformation that will set the energy axis right using that calibration, and you can do whatever works for you, depending on what software you use to read the spectrum. Okay, hope that is helpful. Bye. So since the original video, I've now made an even better full Python script. It does not depend on ImageJ or Fiji anymore, and it will do multiple stacks at a time. So here I've got 3 EDS stacks, and each of them have a BCF file. That's the native Bruker format. And then the raw file, which is the actual raw data that you've been working with. And then the RPL is a text file that basically describes the raw stack, like that. So the way this works now, the new and improved version, you go to a directory that is above the different stacks. So if I go up to this directory, then all of those stacks can get processed at one time. You just want to open a command prompt there, and you're going to run Python from here. So I'm using IPython, but you could also just run the program from the command line using Python if you want. Import make maps from Titan raw. And this code is stored up in the Git repository for the Open NCEM project on Bitbucket. So I'll provide a link for that. And you'll also need to get the tifffile Python script, which will allow you to read and write complicated TIFFs, including image stacks. So then you're going to run make maps from Titan raw, and then there's a function inside, and we're looking for make maps from all stacks under dir. And you just run that, and it will get your current directory, and it'll find those 3 stacks, and it'll just start processing them. So you see that it's making a set of TIFF files. There's one TIFF file for each element, and then it's saving the whole stack as well. And so this was stack 1. And so these are the image files which were just created. These are the semi-quant ones, so that's including the k-factors that were just created. A count sum image will allow you to see the sum of the entire stack, which is kind of like a hot-up image. And then it generates for its own use this cal file, which has to go to the Bruker file and to the RPL file in order to get all of the information it needs to process the stack, and then it stores it in the cal file for future use. And then this stack1.tiff is the actual whole raw data stack, but now in a TIFF format, so you no longer have to go through a rigmarole if you do want to open it up in Fiji or ImageJ. So here's, for example, what the count sum looks like for this stack. And then for the maps, then you can play the usual games. For example, if you want to do RGB, you might do, for instance, FE, NI, S for this particular stack. This is still working on it, doing the third of the 3 stacks, and now it's done. So you can see that's a much faster way to process all of your EDS data, especially if you're acquiring, a half a dozen stacks, or you're trying to do sequential stacks and this sort of thing.